Hi, AP Chemistry students. So we are looking at the basics of bonding, and in this video, we're going to look at the VSEPR shapes, right? So the shapes that these molecules might take. And remember, the VSEPR model is based on kind of like this idea of the balloons. The balloons dictate the shape that these molecules will take because the electrons are essentially pushing each other out of the way, just like how the balloons are pushing each other out of the way, right? They are trying to make a shape that gives them the most space from one another. So we can see like two balloons are furthest away when they are in that linear shape, right? And as we add more balloons, they have to take on different shapes to maximize being as far away from each other as possible. And the balloons will just do this naturally, right? And so that's why it's a good model because the electrons do this naturally. All right, so I'm using the fat molecule shape simulator to kind of show us what we're looking at. So I'm gonna start with 4 domains. All right, what we see here is AX3E. All right, we see 3 bonding atoms and we see a lone pair. And I very deliberately included a double bond and a triple bond because I still want to drive home this idea that that doesn't matter. When we are making that notation, it doesn't matter single, double, or triple bond, right? This is AX3E. And so on the simulator, it tells us the molecule geometry, which for this one is trigonal pyramidal, and the electron geometry, which is the tetrahedral shape. All right, so we're going to look at 4 domains. So if we start with AX4, the molecule geometry and the electron geometry are the same. They're the tetrahedral. And if we look at the bond angles, it's 109.5 degrees. Now, a weird number, but that is the bond angle that allows these domains, these bonded atoms in this AX4 example, to be as far apart from each other as possible, right? If we make any of these bond angles bigger, 2 domains will get too close. So this gives them the most possible space, the tetrahedral shape. All right, now, as we swap out bonding atoms with lone pairs, all right, so as we move to AX3E, the electron geometry does not change, right? Anytime there's 4 domains, no matter what the domains are, the electron geometry is the tetrahedral shape. But that lone pair is empty space. Nothing can exist in that empty space because the electrons are there, all right? So it's kind of like a gap or like a hole. So the atoms themselves now form the trigonal pyramidal shape, right? Still 109.5 degree bond angles, all right? Just with essentially this hole at the top of the tetrahedral. Right? As we move into AX2E2, it's still 4 domains, so the electron geometry does not change, tetrahedral. But the molecule geometry is that bent shape, like a water molecule, right? And remember, the lone pairs, empty space, nothing can exist there, all right? And the bent molecule still retains the 109.5 degree bond angle. And if we have AXE3, right, that is 4 electron domains, its electron geometry is tetrahedral, but there's only 1 bonding atom, is going to be linear, all right? And this is just empty space, those lone pairs. Anytime we have a setup where it's AX1, E whatever, it's going to be linear in shape, right? When there's only 1 other bonding atom, all right? So what we get in the VSEPR model, when we look at this chart, it tells us the total number of domains. Well, for 4, the electron geometry never changed, tetrahedral, right? But as we move from AX4 to AX3E to AX2E2 to AXE3, right? We move from tetrahedral to trigonal pyramid to bent to linear. We have examples, right? These would be great practice if you want to try drawing out those Lewis structures, try to mimic them. And their hybridization doesn't change. They are all sp3. Now, I will talk about hybridization in another video, but I just want you to think right now, sp3, 3p, 1s, that makes 4 total domains, all right? And the bond angle, 109.5. So as we look through this chart, 1 domain is real simple. Generic formula AX, we can't swap it, right? Because otherwise we would have an individual atom if we tried to do the lone pair. So AX, this is the simplest possible geometry we could have. 1 bonded atom, 0 lone pairs. It is linear. H2, hydrogen will form AX. It's S hybridization, bond angle 180 degrees. All right, now two domains. It could be AX2 or it could be AXE. All right, a good example of AX2 is the carbon in the carbon dioxide. All right, it is a linear shape, so it has a 180-degree bond angle. That is the easiest way. They're really far from each other. They're on opposite sides. Two domains, hybridization, SP, 1S, 1P. All right, and the AXE, all right, if we look at the nitrogen, right, the nitrogen would have the notation AXE, right, a bonding atom and a lone pair. All right, it is also linear, nothing really different happening there. So two domains, pretty simple, lines. Three domains, we get the trigonal planar geometry, right? So we can see in this circle, though all the atoms are existing in the same plane. We could think of it as like the XY plane, right? They're all existing there. It looks like a Mercedes-Benz sign, and it is a 120-degree bond angle. All right, so the electron geometry is trigonal planar. All right, and how does it change when we move from AX3 to AX2E? All right, when we get that gap for the lone pair, it takes on a bent shape. All right, and the interesting thing here, all right, the AX2E bent shape has a 120-degree bond angle, whereas the AX2E2 has the 109.5. All right, three domains, we're going to call them SP2 hybridized. All right, and AXE2 is that linear shape. All right, that happens anytime there's only one bonded atom and the rest of the domains are lone pairs. All right, and there are 5 and 6 domains: AX5, AX4E, AX3E2, AX2E3. This chart has a footnote that I did not include. There are certain combinations of X and E that are not allowed. They're just not stable, right? AX6, AX5E, AX4E2, right? There's no AX3E3, for example. That doesn't exist, all right? 5 domains is based on the trigonal bipyramidal shape, which has 90-degree and 120-degree bond angles. AX6 is based on the octahedral shape, which has 90-degree bond angles, all right? 5 domains, SP3D, 1 plus 3 plus 1, 5. All right, 6 domains, SP3D2, 1 plus 3 plus 2. That gets us to 6. The College Board says over and over again, you do not need to know the geometry of 5 domains and 6 domains. It is here. I highly recommend you jump on that PhET simulator and play around with these shapes, get a feel for them, you know, see what's going on with the octahedral, see what's going on with some of the funky shapes. Here is a seesaw shape, all right? But the College Board is saying you don't need to know those shapes. You're gonna need to know tetrahedral, bent, trigonal pyramidal. You're going to need to know the bond angles of 180 degrees when it's linear, 120 degrees when it's 3 domains, 109.5 degrees when it is 4 domains. All right, so those are the geometries that we were talking about. And here, this does a great job of showing us the lone pair is just empty space. There's nothing there. So we can see how nothing is included there. I mentioned that several times, but this slide gives us a great visual of that.